For those of you who are new to the System Dynamics Society, I'd like to introduce myself. I'm a retired secondary school mathematics teacher who taught system dynamics for 20 years to my high school mathematics students, and also taught a year-long system dynamics modeling class to my high school students. And let me tell you, those students can do this. They are very powerful thinkers, and we really need to tap what they can bring to society. When I retired from high school teaching, I had been infected with the system dynamics bug, so I went back to school and got some additional training. I received a doctorate in system science and subsequently have done professional development with teachers and professors. I've always been interested in global climate change, as it is an extremely important topic, and I was wondering if I could build a model in the free System Dynamics, Stella Online, software that dealt with global climate change so students could build this model in the free software. I wanted to construct a lesson that perhaps an environmental science teacher could use as part of a lesson on global climate change. So that is what this paper and presentation is all about. I do believe I was reasonably successful in building a small model, and I want to talk to you about the details of that model and lesson. We can all agree that all students need to understand the dynamics of global climate change. In the United States, there are some cross-cutting national standards for teaching pre-college science that work in our favor. There are some science standards that are to be emphasized across all different science disciplines. Those cross-cutting goals include systems modeling, cause and effect, stability and change patterns, energy and matter. These goals are designed to guide instruction in all sciences. And there are some specific disciplinary core ideas that specifically identify global climate change as an important topic to include as part of instruction. But states can create their own standards for each science teaching discipline. How well are the states doing in teaching about global climate change? There is a 2021 book by Katie Worth, an investigative reporter who has won many awards, that has been recently published, Miseducation: How Global Climate Change is Taught in America. Ms. Worth did some analysis on how well the U.S. is actually teaching global climate change. Here are just a few key points from her book. A survey in 2021, a quarter of Americans under 18 declined to call climate change an emergency. In 1997, after the Kyoto Climate Summit meeting on global climate change, the American Petroleum Institute had a goal that was stated as, "Victory will be achieved when the average citizen understands the uncertainties in global climate change." At that point, they wanted to specifically target this message to teachers and students. So they did not want to deny, per se, global climate change, but to say maybe it's a problem. That strategy would not evoke strong opposition to the message. In 2019, a survey of 1,427 science teachers indicated that half of the teachers did not spend much time teaching global climate change at all. Since this is all science teachers, you might expect a physics teacher might not teach much about climate. Of the teachers who did teach climate change, a third of them believed warming was natural, and they taught that many scientists believe that this is a natural occurrence. And 2/3 used debates about global climate change as part of their instructional method, which scientists equate to essentially climate denial. In this book, global climate scientists and science educators agree on 5 big facts about global climate change that need to be taught. It's real, it's us. Experts agree on this particular problem. It's bad, but there's hope. So that should be the core of an instructional approach about climate change in pre-college education. The last point from the information in her book that I think is relevant for this particular lesson is information from Frank Niepold, a senior manager on teaching about climate for the National Oceanographic and Atmospheric Association. He interviewed pre-college students. Today, most climate change lessons are about 99% presenting the problem and 1% presenting the solution. Students want 20% on the problem and 80% on the solution, which makes sense. They want hope. They want to know what they can do to have hope. Now I'm going to talk about the system dynamics model that I would have students build in a global climate change lesson. This would not be the first system dynamics model that students would have built in the course. In an environmental science class, this modeling lesson might be used in the second half of the academic year. Students should have experience building simple models first, especially population models, before they even get to this point. Recall that there are 4 icons that are used to create system dynamics models. Stocks, shown as a rectangle, represent those quantities that accumulate in the model and whose value we want to track over time, like population in a country, or money in a bank account, or water in a bathtub. Flows, shown as pipes with 1 or 2 arrowheads, represent the rate at which the stock is changing value, or represent the variables that directly increase or decrease the value of the stock. A birth flow would increase the value of a population stock. Converters, shown as independent circles, will usually hold constants. Connectors, the little red arrow, will specify the links between components. These modeling components are connected together in a plumbing type diagram. If one wants to increase the value of the stock, say volume of water in a bathtub, this can be done by increasing the water flowing into the tub from the faucet or decreasing the amount of water being pumped out of the tub. This particular model has 3 stocks in it. As you might expect, there is a population segment. I will start with that segment. I went to respected internet sources for data. I found the data for global population and put a trend line on the time series data in Excel. Students are taught to put trend lines on time series data in some algebra classes in the United States. To get the behavioral tendency in the data, and as long as they know how to select a reasonably correct pattern to use for this trend line, they can get a reasonable equation that represents the behavior over time pattern for the data. For this model segment, I used the original population for 1950, that the model starts in 1950. And then I used the net growth fraction from the trend line. This is the first segment of the model dealing with population. I took the net growth fraction and split it into 2 parts, so I would have a birth fraction and a death fraction. I just looked up the 1950 global birth fraction on the internet and then calculated the death fraction using the birth fraction and the net growth fraction. Stella is the preferred system dynamics modeling software for pre-college education. I used their free Stella Online software as a target environment for my pre-college model building. The free web-based Stella Online software allows a maximum of 3 stocks and a maximum of 20 icons for model simulations. I use this as a guide because it provides an opportunity for teachers to be able to use system dynamics models without additional expense in their classroom if their school has technology like laptops or tablets for students to use and a connection to the internet. There is a global temperature segment for this model. This segment uses NASA data. I took the data and selected an exponential trend line. The population is growing exponentially, and we will use per capita CO2 emissions to influence the change in global temperature. So the temperature should change exponentially due to CO2 emissions. I will use the 1950 global temperature, actually 13.8 instead of the 13.83 degrees Celsius. And I will use the net temperature change fraction from the trend line equation. This slide shows the simple global temperature segment of the model using the 1950 global temperature and the net temperature change fraction from the previous trendline analysis. If the net temperature change value is positive, the biflow will act as an inflow and increase the value of the global temperature stock, as is the case here. The next step is to connect these two segments. I used a dimensionless multiplier, a graphical converter, to control how the ratio of the current global temperature compared to the global temperature in 1950 will alter or modify the death fraction of the global population. I decided a global temperature ratio close to 1 would probably start gradually to increase the death fraction. As the global temperature ratio increases, the death fraction increases more dramatically. The shape of the graph was guided by the projected UN global population for 2050 and 2100. Next, I will show how I added the calculations for per capita CO2 emissions to the model diagram. I decided to use CO2 per capita global emissions from 1950 to 2020 as an impact of global population on global temperature change. But the trend line did not fit the time series CO2 emission data well. Notice there was a significant drop in CO2 emissions in 1990. There is a New York Times article quoting a World Watch document suggesting that this decline was probably due to the collapse of the economies in 1990 of the USSR and countries in Eastern Europe that used significant coal to power their economies. So I decided to split the CO2 emission trend line into two separate, very simple trend lines, one for 1950 to 1989 and the other from 1990 to 2020. These were the linear trendline equations for each set of data. I defined the per capita CO2 emission data using an if-then statement. The first trendline equation for emissions from 1950 to 1989 and the second trendline equation for emissions from 1990 to 2020. Although if-then statements are frowned upon in system dynamics models, that definition seemed reasonable for this situation. The per capita emissions were multiplied by the global population. The total CO2 emissions each year were then compared to the total CO2 emissions in 1950 in a graphical converter, and that information determined the impact of CO2 emissions on the net change in global temperature. The dimensionless multiplier here contains the point 10 because I wanted the global temperature to have a chance to drop if the emissions were reduced to lower than 1950 emission levels. I think the upper right shape of this dimensionless multiplier is probably too conservative, but the shape was informed by trying to match the Intergovernmental Panel on Climate Change 2040 projection for global climate change. I tried to be conservative in the design of each of the dimensionless multipliers used in this model. The paper contains an explanation of the assumptions that influence the design of each of the dimensionless multipliers. This graph contains the global population, green, and the global temperature, red, graphs from 1950 to 2150 produced by the model. The light yellow graph from 1950 to 2020 is the historical global population, and the jagged purple graph is the historical global temperature from 1950 to 2020. This grid shows the UN global population projections for 2050 and 2100 and the IPCC projection for global temperature for 2040. The model captures these projections well. The shape of the dimensionless multipliers allowed me to capture these projection values reasonably well. I wanted to see what behavior might be produced by the model if a policy to restrict CO2 emissions was implemented. This graph shows that if CO2 emissions were reduced by 10% of 2022 emissions by about 2100, global temperature would stabilize at around 17 degrees Celsius, which is 62.2 degrees Fahrenheit, around 2150. The global population stabilizes at around 11.2 billion people in 2150. How to use the model at this point as part of a lesson on global climate change. Students can build the model previously shown in the free Stella Online software. Then the teacher could give each student a copy of the model diagram. The teacher could ask students to pick a partner and research a climate change issue. Each team could sketch one stock with its necessary flows for their topic. Each team would sketch their added model component on the paper and attach it to the appropriate places on the core population temperature model diagram. Then each team would display and explain their edited model diagram and how they think it would impact the population and temperature. Essentially, what the students are doing is unpacking the impact on population and or temperature that is captured in each dimensionless multiplier. This slide shows some possible topics students could use to research on the impact of rising global temperatures. The lesson could terminate with the information described in the previous slide, or the teacher could decide to demonstrate a potential addition to the model, the change in easily accessible global potable water over time. Here, the one stock added is easily accessible potable water. It is increased by regeneration and decreased by consumption. On the consumption side, the global population is consuming the water. The total consumption for 1950 was found on the Our World in Data website. It represents human water consumption and potable water used for industrial and agricultural purposes. That value was divided by the global population in 1950 to produce the 484 cubic meters of water consumed per capita. The regeneration fraction value was a guess. This value produced either steady state or slightly increasing easily accessible potable water stock values from 1950 to about 1980. The initial stock value came from the U.S. Bureau of Reclamations in California. The value on the website for approximate global water resources had to be converted to easily accessible potable water and had to have units converted to cubic meters. This slide shows how the easily accessible potable water model segment is added to the previous core climate change model. Global population is connected to water consumption. Global temperature is compared to global temperature in 1950, and that ratio in a graphical converter modifies the regeneration of potable water. Higher global temperature reduces regeneration. There is a per capita water stress level below which normal daily living becomes negatively impacted. This value includes both human water consumption and water needed for agricultural and industrial use to support a person. The current easily accessible potable water level is compared to the total population water stress level. Based on that ratio, in a graphical converter, a multiplier is sent to the modified depth fraction to change even more the depth fraction based on the impact of the amount of easily accessible potable water that is available. The total population water stress level also impacts how much water people can consume. Less water means less consumption. Moreover, the consumption of potable water per capita has increased by 1.8% for the last 100 years. So the water consumption outflow is a super exponential process, which does not bode well for humans on this planet. This slide shows business as usual with the easily accessible potable water concept added to the global climate change model segment constructed earlier. The blue graph shows the global quantity of easily accessible potable water. The dashed brown graph shows the total water consumption outflow. Notice the decrease in water consumption in the dashed brown graph from 2020 to 2025. Research indicated that the increase in per capita water consumption has reduced from 1.8% per year to closer to 1% per year in recent years. The model keeps the increase at 1% after 2025. Water has a significant impact on the size of the human population that can be supported. as a convenient data point for comparison over the next few graphs. This business as usual graph has global population in 2150 at 8.7 billion people and falling. This graph just shows the UN population projection for 2050 to 2100 and the IPCC projection for global temperature for 2040. The current model output still captures these projections well. Now let's look at the possible outcome of 3 potential policies to try to improve the future scenario for the global population. In this scenario, we reduce CO2 emissions as before and see that global temperature levels off. Global population in 2150 for this policy rises to 8.9 billion people. This policy reduces the yearly increase in per capita water consumption, which is not due to population increase, to essentially 0% by 2080. Here, the global population in 2150 is at 10.1 billion people and dropping slower than business as usual. Finally, this graph applies both reduction in CO2 emissions and reduction in per capita increase in water consumption of the previous 2 slides. It shows a global population in 2150 of 11 billion people, which is decreasing very slowly. But looking at the behavior of the model is not enough to bring home the lesson about future problems and water consumption. For this lesson to be most impactful, we need to include 2 more lesson concepts. The first is to include the idea that loss of access to potable water is not felt by everyone on the globe at the same time. Currently, Saudi Arabia gets 60% of its potable water from desalination plants, but these plants are expensive to construct and produce a significant amount of brine for each liter of water, and brine is a pollutant. So what are the options for poorer countries? Students should research the places globally that will be affected most and when. What is the responsibility of countries that have lots of water to other countries? The second part of the post-modeling lesson should include student agency. Recall that students want lessons on climate change to be 20% about the problem and 80% about the solution. Students do want to do something to protect their future. They should research what other countries are doing to conserve water. Young students could focus on water conservation in their families, like taking shorter showers, not letting water run out of the faucet unnecessarily, talking to their parents about changing their lawn to incorporate more native plants so it requires less water, and or having the family eat less beef and drink less soda and beer. Middle school students could focus on water conservation at their school, establishing a student action group for addressing water conservation at the student's school, trying to figure out how to use wastewater or capture rainwater, setting up ways to measure water consumption and publicize this to students, changing cafeteria food to less food that is water intensive to produce, beef and nuts, etc. Secondary school students should focus on water conservation in their community, going to the local water department to find out which businesses in their area use the most water each month, and perhaps working with the city council to create an award for businesses who reduce their water consumption the most over the year. Reducing contamination of water supplies due to extreme weather conditions, also having business set up water level monitoring devices to keep track of water consumption, trying to get businesses to use more precipitation capture devices, discussing the importance of changing diets to ones that are not so water intensive to produce, and discuss the need for population control within social science, health, and environmental science classes. Population control, however, is an explosive issue. We must provide ways to give students hope for their future. As parents and educators, we have a responsibility to our children. You can find the paper for this model with the equations for the core model at this web address. Thank you.